Thank you very much, and thanks to the organizers for the invitation to come here to Bangalore. It's my first time here. It seems great so far. So yes, what I want to talk about today is a geometric flow for submanifolds. So suppose that I have some submanifold L of dimension n inside Euclidean space of dimension capital N, or you can take a Riemannian manifold, and then, as we know, this conference is all about, you want to think about the volume of the submanifold and think about critical points for volume. So if we look at the negative gradient flow of volume, then what is that? That is called the mean curvature flow. So that's very long to write, so I'm not going to write it ever again. I'm just going to write MCF, mean curvature flow. And what is it as an equation? It says that if I look at a family of submanifolds, L depending on time t, then the variation of L with respect to t should be H, the mean curvature vector. Okay, so obviously I don't know what you know and don't know about this already. So please stop me, interrupt me, ask questions, say, oh, we know this already, please speed up. Do that, okay? Great. So now the problem is, there's a problem with this flow. The problem is that it's badly behaved in general if the dimension is more than n plus 1. So if you're looking at more than hypersurfaces, this is usually not a very good flow equation. Okay, so a solution is consider a class of submanifolds, so not all submanifolds, but a class preserved by the mean curvature flow. So what we're going to do is we're going to take n to be twice the dimension. So when n is bigger than 1, this will be in the bad setting in general. And then we can define on R2n, we're going to take coordinates x1, y1 up to xn, yn. But we can also think of that as cn. So we can think of that as complex coordinates x1 plus I, y1, all the way up to xn plus I, yn. Now, on this even dimensional Euclidean spaces, you can always construct a non-degenerate 2 form, which I'll always call little omega, and it's dx1 wedge dy1 plus all the way up to dxn wedge dyn. And you have a complex structure, which I'll call J, which is just multiplication by I. The complex number I. Okay, and then I can already tell you now what Lagrangian means. So Ln in R2n is Lagrangian. If and only if, when I restrict the 2 form to L, I get 0. And it turns out that's the same thing. If you look at this formula and you think about what J does, that's the same as saying if I take the tangent space to L, any tangent space to L, and hit it with J, okay, then what do I get? Well, if I did this in dimension 1, right, if I just had a curve in the plane, say, and I took something tangent and I hit it with I, then it would be at right angles, right? Every single time. So what I want is the same thing to be true in higher dimensions, and that's what the Lagrangian condition says. It says if you take J of any tangent vector, it's a normal vector. And so this example here shows that all curves in R2 are Lagrangian. But this is, as I was told, supposed to be a pedagogical lecture. You're supposed to be learning something and perhaps then doing something. So I'm going to set you an exercise. And the exercise is this. So consider a map F going from Rn to Rn. Show that the graph of F, so that's the set of x plus I f of x, so x is an Rn contained in Cn, is Lagrangian if and only if there exists a function small f from Rn to R such that f is the graph. Okay? So that's the statement. So Lagrangians, they look like they're n-dimensional objects, right? They're vector valued. You need n things to describe them, but actually, if you think of them locally as graphs, they are defined by a scalar function. That's actually very special. That's like hypersurfaces. They're defined by a scalar function. So you might hope that they're better behaved from that reason. This exercise also tells you that there's loads of Lagrangians, right? Give me any function from Rn to R, I get a Lagrangian. Right? So there are loads of them. Okay, now what I want to do is I want to introduce a new object. So let big omega, so we had a little omega, now we have a big omega, and this looks a lot like the volume form on Rn, but it's an n form. So this is often called the holomorphic volume form, or complex volume form. And a little lemma that you can prove is let Ln be contained in Cn, then omega restricted to L, if I take its norm, it's always less than or equal to 1. So this form, I restrict it to the Lagrangian. I say, how big is it? It's always less than or equal to 1. Is it okay? Does it make sense? I just evaluate it on unit tangent vectors, right? I just take a unit tangent and I evaluate it, and I take the size. I get a number less than or equal to 1, and equals 1 if and only if L is Lagrangian. So that's another little exercise for you to show that this is true. Okay? So Lagrangians are the things on which this form restricts to be of unit size. Okay? Now, what's the corollary of that is I can make the following definition. Suppose that my L is oriented Lagrangian. Then I know that if I take omega and restrict it to L, then I can compare it to the volume form on L. This is of unit norm. This is of unit norm. So there must be a unit complex number that relates them, right? E to the I theta. For e to the I theta, a function from L to S1, which is called the Lagrangian angle. Theta is called the Lagrangian angle. All right, so why did I bother to tell you about the Lagrangian angle? Why is that thing interesting? And what is the Lagrangian angle anyway? Well, if I take my curve again, then the Lagrangian angle is just the angle that I make with the x-axis, with the horizontal axis. That's what the Lagrangian angle is. So it's nothing mysterious. Okay? Now, something that you know very well, I hope, from curves in the plane is what's a way to calculate the curvature of the curve? Well, what I can do is I can differentiate this angle. Right? If I take the derivative of this angle, that enables me to compute the curvature of the curve. So you might hope that the same thing is true here. Maybe if I take the derivative of the Lagrangian angle, it gives me some curvature quantity related to my Lagrangian. And the answer is yes, so that if L is Lagrangian, well, I mean, it's not a secret what the answer is going to be because we know what this lecture is about. It's going to be the mean curvature. The mean curvature is the gradient of the Lagrangian angle, but of course you have to turn it into a normal vector, so you hit it with J. Okay. So this is the key formula that makes everything work. Any questions? Where is this? All right. And what we also notice is a corollary is that if L is connected, then L is a minimal Lagrangian if and only if theta is constant. Right. Yeah, because the gradient's 0, so theta has to be constant. So that leads us to a definition. L is special Lagrangian, Ln contained in Cn, is special Lagrangian if the Lagrangian angle is constant. Turns out, it comes from that lemma that I said about the norm of big omega. That's the same as saying that the real part of e to the minus I theta naught times omega is the volume form on L. That comes straight out of that lemma over there. And that same lemma tells you it's the same as saying that omega restricted to L is 0, so it's Lagrangian, and that the imaginary part of e to the minus I theta naught omega restricted to L is identically 0. Go for it. They're not quite the same because if you had multiple connected components, then they would not be the same. So for example, if you take two lines in the plane with different angles meeting at the origin, that would not be special Lagrangian, right? Because it doesn't have a single constant angle, but each separate line is. So it's connected, it's the same, absolutely. Minimal Lagrangian, special Lagrangian are the same. That's right. And now, what we can prove is the following very nice theorem. Unfortunately, I don't have time to prove it, but what you can see is that if L is special Lagrangian, which I will abbreviate to SL, if L is a compact special Lagrangian, then L is volume minimizing. In its homology class. Okay. This is a theorem due to Harvey and Lawson. Now, immediately, this should actually make sense to you because you know there are no compact minimal surfaces in Euclidean space. So working Euclidean space is not going to be very interesting for studying compact special Lagrangians. So I have to tell you about what is the right class of manifolds to look for compact special Lagrangians. So this is a definition. We say that an n-dimensional complex manifold, so a complex n-manifold, is Calabi-Yau if there exists a 2-form, a 1-1 form omega on M, an n0 form capital omega. So the notation should make sense to you. It's going to be the same as the little omega and the big omega I had before, with them both being closed, and for all points in M, there exists an oriented isomorphism. Okay, so I'm going to write down the definition, but then I'll explain what I mean. TPM to Cn with, if I pull back the Euclidean omega, I get this omega, and I pull back the Euclidean big omega, I get this big omega. So what it says is, it looks like Cn, the standard Cn at every point, except that, and what I want is I want this little omega and big omega to somehow vary constantly across the manifold. So what you see is actually I asked for them to be closed, but it implies that if G is the metric you get built out of omega and J, then these forms are actually covariantly constant for the Levi-Civita connection of that metric, and the metric has holonomy contained in SUN, which means that the metric is Ricci flat. So these are Kähler manifolds and Kähler. These are Kähler Ricci flat manifolds. Any questions about that? They're allowed to be non-compact. They can just be Cn. Yeah. I'm allowing Cn for this definition. Yeah. But the point is that there are interesting non-compact Calabi-Yaus that can have compact special Lagrangians. So we'll see that in the next talk when I talk about examples. Okay. So we'll postpone that for now. And instead, I want to state the sort of main idea, the sort of main question that we have is the following. So suppose that we have some Lagrangian that maybe looks a bit like this, and we run the mean curvature flow, then the question is there a Lagrangian mean curvature flow? So if I start a Lagrangian and run the mean curvature flow doesn't know anything about Lagrangians. Right? It's just a purely Riemannian statement. It doesn't know that I have a 2-form there. And this is the theorem. Smotzik, which says if that L is a compact Lagrangian in M Calabi-Yau, then mean curvature flow preserves the Lagrangian condition. Okay, so indeed I can scrub out the question mark and it's true. Right? This leads to the notion of Lagrangian mean curvature flow. So it's nothing different, it's just the mean curvature flow you had before, but it happens to be one that it's always Lagrangian. Right? All the submanifolds are Lagrangian. They start Lagrangian, they stay Lagrangian. But it's very important that your Lagrangian is compact, or at least has controlled behavior at infinity, because the proof is via the maximum principle. So you have to be able to apply the maximum principle properly, but that's the idea. So the key steps are the following. The key points. Oh yeah, the question here. So, oh yeah, sorry, yeah, the equation. Yeah, exactly, please, yeah, thank you. I was gonna do that, let me do it now. So yeah, now dl by dt is h, the same equation, exactly the same, except now I know that h is actually j grad theta, right? Because of this. And what this means is that Lagrangian mean curvature flow is of the form dl by ds is j grad hs for a function h. This is called a Hamiltonian isotopy. If h is single valued. So the flow is of this form, but it's always a Lagrangian isotopy. That just says it looks like this, but it's actually a Hamiltonian isotopy whenever you know that theta is actually a single valued function, which it may not be, right? Because I only defined e to the I theta. That's all I defined. And then I said there's this Lagrangian angle theta, but what I pushed under the rug is that this could be a multi-valued function. It won't be except when theta is single valued. So that is a very important definition, which I'll make now since we're talking about it. We say that a Lagrangian L is 0 Maslov if I take d theta, that's a well-defined cohomology class in L, this is 0. That's what I'm asking. i.e., theta is a single value function. That's all I'm saying. So exactly in that case, and that's preserved by the flow, that condition, 0 Maslov, because it's a topological condition, so it's preserved. So if I start like that, I stay like that, and then it is a Hamiltonian isotopy in that case. Okay, so let me just finish by saying what the key points are to prove that theorem of Smotzik, and then I will stop. Okay, so the key points are the following. So there are 3 key points. The first is that if I do H contracted with omega restricted to L, and L is Lagrangian, then this I know is, okay, it's minus d theta if you do it. So if I take d of this, I get d of minus d theta, and that's 0. So that's one of the key things that you have to know. And so this will always work. This always works in the Calabi-Yau settings. It's got nothing to do with being Euclidean space. The next thing is that it uses the maximum principle applied to the function, which is you take omega restricted to LT and square it. That's your function. It depends on time. And the other thing that you have to notice is that so for short time, yeah, that's my time up, isn't it? For short time, Oh, that's somebody's phone. Okay, so, okay. Oh, but this thing says 0. Oh, okay, all right. Well, okay. You tell me what I should do. Okay, so that's fine. So for short time along the mean curvature flow, what can we say? Well, what we can say is that if I just start a Lagrangian and start the mean curvature flow, I don't know that it stays Lagrangian. But one thing that I do know is that for all points in LT, remember this is some short time. Now before, this is what we knew that these two spaces were orthogonal to each other, right? We knew that these two spaces were orthogonal to each other at time 0. Now, being orthogonal, that's not an open condition, right? That's a closed condition. But being transverse is an open condition. So then I know, for short time, I know that this is going to be true. Right? For every point on my manifold, if it's compact, right? If it's compact, I know for every point on the manifold, I know that this is going to be true. And these are called totally real submanifolds. And what this implies is that we can do all of these nice calculations, in particular, if Z and W are normal vectors on LT, then omega Z and W is actually going to be the same as omega of J x perp, J y perp, for some tangent vectors x and y, and that's going to be omega of xy plus omega of jx tangent, jy tangent. It doesn't really matter what the formula is, although I would urge you to convince yourself that this is true. So this is for xy tangent. But the point is, I don't really care what the formula is, but what I do care is that if I have two normal vectors and I evaluate omega on them, it's the same as evaluating omega on two tangent vectors. So that means even though I might be computing something on the normal bundle, I can relate it to something on the tangent bundle, i.e. to this thing again. And what you'll get is you'll get an equation that looks like d by dt of ft is less than or equal to the Laplacian of ft plus b ft for some b greater than 0 constant. And that's what you'll apply the maximum principle to. Okay, so have you decided whether I have half an hour or an hour? It's an hour, okay. It's just that on the schedule it said half an hour, but that's okay. That's okay. That's all right. That's all right. I will now make do and mend. That's all good. No, but this is good. Okay, so at this point, that's a good midpoint. Are there some questions? Because it's gone fairly rapidly. Yeah, please. Yeah, that's a very, very good point. Yes, we do. That's what I wanted to talk about somehow next time, and also in my research talk. But yes, we do know in some cases it's going to actually work. So what do I mean by work? So I didn't finish my diagram here, so let me come back to it. What would you hope would happen if you'd run the Lagrangian mean curvature flow starting with some Lagrangian? I mean, in your dream, you would hope it to exist for all time and converge to a minimal Lagrangian, i.e. a special Lagrangian. That would be the dream. So maybe it converges, schematically to this. Actually, let's make it look round. To this special Lagrangian. So maybe it does that. In some cases, that is what it does. Okay? You can prove there are cases where you can start with a Lagrangian, the flow exists for all time, and converges to a special Lagrangian. But something else can happen. So I drew it like this, because if you make this neck too small, then what you might imagine is that it breaks up. See, it has a singularity that forms after some finite amount of time, and then you have to continue the flow past the singularity, and then you might ask a union of special Lagrangians, maybe. Can we get a decomposition? After some finite number of singularities, can we always decompose something into special Lagrangians? Right. Now we know that that may not be possible. Like if you take just mean curvature flow and just take a sphere in Rn plus 1, then that will just shrink to a point, right? So it doesn't head to a minimal anything. But it does head to something, if you rescale, it heads to something with constant mean curvature. So you could also ask for this. You could also ask for things that behave in a nice way under the Lagrangian mean curvature flow. Maybe they just self-similarly shrink. Maybe that's one of the pieces. Right? So what you're asking for in general, so here in general, we want, actually I'll write this somewhere sensible. Go over here. Okay, so what's the aim? So this, I think, comes to your question about the long time existence and convergence business. The aim is that LMCF decomposes an initial, possibly compact Lagrangian into canonical pieces after a finite number of singular times. Okay? That's the aim, right? That's what you hope, is that you start this process, you try to make the volume smaller and smaller and smaller, and each time you break off some bit that you know, and you say, that's good, that's say a minimal piece. The other piece I don't know, I run the flow again, starting with that piece, hope that goes somewhere nice. And you keep doing this over and over and over until eventually it stops. And there are cases where we know that this works. Yeah. There are cases where we know that it works, but there are many cases where we don't have any idea. So most of the time we don't know, but sometimes we know that it works. Yeah. More questions? By theta being single valued here, yeah, I just mean that, i.e., so this doesn't say that H is well defined. This says that gradient H is well defined, right? So what I mean is that H is a map really to H. So in general, H is a map from L to R mod 2 pi z, right? In general, up to multiples of 2 pi, integer multiples of 2 pi. So being single valued means we can choose H actually just to be a map into R, genuinely a map into R. So for example, suppose I just take a circle in the plane. Right? What's the Lagrangian angle? Well, it's just going to be this, basically. Right? This is clearly not a single value function. Because if I come back to where I started, it's gone up by 2 pi. So the Lagrangian angle is just the angle, but that's not a, it's not quite because it's the angle the tangent vector makes, so it's actually theta plus pi by 2. But anyway, it's the roughly speaking, it's the angle. But we can see it's definitely not single valued. Good. Okay. So, all right. Let me then now talk about some other nice formulas that are very useful in the Lagrangian mean curvature flow. Okay. So I mentioned this zero Maslov thing. So we know that that condition is preserved along the flow. So I'll say that here. So 0 Maslov is preserved along LMCF. So that means, remember, what did special Lagrangian mean? Special Lagrangian meant that the Lagrangian angle was constant. Well, that's definitely single valued. So if we want to have any hope of converging to something special Lagrangian, we better start with a single value function. Right? So preserved along MCF, therefore, we need L to be 0 Maslov to get to hope to get convergence to a special Lagrangian. So already that says we only look at 0 Maslov Lagrangian mean curvature flow. Okay? Is it okay? Is there something I wrote that you can't read? Or is it right? Okay. If we want to get convergence to a special Lagrangian, then we have to take this 0 Maslov condition. And so it would be nice to know, how does the Lagrangian angle vary along 0 Maslov Lagrangian mean curvature flow? So under 0 Maslov LMCF, I want to ask, what is the rate of change of the Lagrangian angle? And it is just, it varies by the heat equation. So that's really nice. Right? That's really nice. In particular, you'll see that the following class of submanifolds is preserved. Therefore, corollary, so if I make the following definition, we say that L is almost calibrated if the supremum of the Lagrangian angle minus the infimum of the Lagrangian angle is strictly less than pi. So, and then the proposition implies this is preserved by LMCF. So this fits with our philosophy of finding good classes of submanifolds that are preserved by the mean curvature flow. We found another class which is preserved, which is good. So what does this mean? This sup minus inf is less than pi. Well, what it means is that the curve, if you take a curve in the plane again, it can't turn by more than pi. So that means it has to look something, look something like this. It can't turn by more than pi. In particular, it can't have an immersed point, right, for sure. Right? It has to be embedded, but it's stronger than that. Right? In particular, it implies embedded. So as an example, almost calibrated curve implies embedded arc. Okay. Right. So I said that we had these singularities that could form along the mean curvature flow. And so a natural question is to ask, what do the singularities look like? So a natural candidate for a Lagrangian mean curvature flow singularity is a self-shrinker. So what does this mean? This means that if I take the mean curvature vector, h, it's equal to minus the position vector on Euclidean space, take its normal projection and divide by 2. So x here is just the position vector on Cn. So why is this thing good? This means that if L is a self-shrinker, then the square root of minus TL satisfies the Lagrangian mean curvature flow. So this is, of course, this doesn't make sense unless T is negative. This is the same thing. This is if and only if. So what's happening is defined for negative times, as T is going to 0, everything is going to the origin. Right? So it's shrinking down. It's staying exactly the same, apart from its scaling in size. At T, it's -1, it's where it started, and it goes just down to 0. Okay. So that's the statement. Okay. So that would just be like a sphere in Euclidean space. Unit sphere. That would just be the thing. So that's your guess, right? That would be a nice guess, but there's a theorem that says that this is actually not right, which is very surprising. So I think this was first proved by Wang, and then improved by Andre Neves, and it says the following: if you have that L is a 0 Maslov smooth self-shrinker, then L is a plane. So that means it's not singular at all, right? It's not actually giving you a model for a singularity. So you can't have a shrinking sphere. That's already very different from what you're used to from the regular mean curvature flow. There are no shrinking spheres. Those don't exist. Okay. And so, and the key, I'll just say it because I don't have time to go through it, but the key point is you just use what's called Huysgen's monotonicity formula. Maybe, did we see the monotonicity formula for minimal surfaces so far this week? Maybe not. Okay, oh, you did, great. Well, there's an analog for that in the mean curvature flow, which says that a weighted volume is monotone along the flow. And so you can use Huysgen's monotonicity formula for the Lagrangian angle squared. Okay. So the Lagrangian angle satisfies the His equation, because what you see is that if I take the derivative of the Lagrangian angle squared, I get the Laplacian of the Lagrangian angle minus 2 times the gradient of theta squared. And this term is going to force theta to be constant. And that's going to be the thing that's going to be a problem, because if you're going to have constant theta, and yet you're supposed to be a self-shrinker, you've got to be minimal and shrinking at the same time. That's impossible, unless you're just a plane. That's what it's going to tell you. Okay. All right. So there are no 0 Maslov self-shrinkers. So we're going to have to work a little bit harder to think about what singularities are going to look like. But let me be a bit more precise about what I mean by what singularities look like. Let me just get my notation right. Oh, actually, I should say one thing before I do that. So let me just make a definition here, which is going to be, actually, I'll do it over here. This is the last piece of notation that I will introduce. I'm going to let lambda be the following object. It's the sum of xj dyj minus yj dxj. J equals 1 up to n on R2n. And why did I do that? What's good about that thing? Well, what happens if I take d of this lambda? I'm doing this slowly enough that you could have done it before I write it down. Well, if I take d of the lambda, I'm just going to get 2 lots of omega. So that means that if I have a Lagrangian, then if I take this lambda and restrict it to L, it's a closed form on L. It's a closed one form. That means it defines a cohomology class on L. And we already had a cohomology class in this same degree, the class of the Lagrangian angle, right? D theta was also in here. And so this gives me 2 definitions. One, we say that L is monotone if the Lagrangian angle, the class of the Lagrangian angle, is a positive constant times the class of the times this. Okay. Oh, in case you care, lambda is called the Liouville form. Okay. Now you can see there's a very special case. What if my d theta were 0, right? If d theta was 0, this is a positive constant, it would force this to be 0. And so that's a special case. L is called exact, for obvious reasons, if this class is 0 in the first cohomology. Okay, and then what I wanted to say is that, okay, you can't have 0 Maslov self-shrinkers, but what you have instead is the following lemma, which I'll leave as an exercise for you. It's very easy. So this is an exercise they should definitely do, is that Lagrangian self-shrinkers are monotone. So that's an easy exercise using the definitions to prove that. Okay. Right. Now, I just want to finish by talking about, and this time I really am finishing. I think this is the real end time now. So now I'm going to finish by talking about what the singularity models could look like by giving you the notion of blow up. So let LT, t in 0 up to t, be a Lagrangian mean curvature flow with a singularity at x0, let's just say in Cn, but it doesn't really matter. At x0t, where t is finite. Okay. Then we say that let sigma j be some numbers that tend to infinity. Then what we can do is we can look at the following objects. We can consider Ljs to be sigma j t minus sigma j to the minus 2s minus x0. So what am I doing? I'm centering myself at x0, I'm rescaling by space, and I'm rescaling in time. I'm doing. So I'm zooming out and slowing down. That's what I'm doing. So S is in, I guess, minus sigma j to the minus 2 t t or something, up to 0. Okay. And then what's going to happen is I can send j to infinity, and along a subsequence, this will converge to some L infinity s, which is called a tangent flow, defined for all s negative. So note, it's very important that this is only a subsequential convergence. So L infinity s need not be . You can also do something slightly different, is you can do the type 2 blow up. So then you can also define, if you have some points xj tending to x0, some points tj tending upwards to t, such that the supremum of the second fundamental form is realized at xj tj, then you can do the same trick. You can define ljs. It's the same formula, pretty much, except instead of t, you put tj, and instead of x0, you put xj. So it's exactly the same. You just change it slightly. It just means I'm not centering at a particular point. I'm allowed to move the point around which I'm focusing my attention. And this, again, subsequently converges to a solution defined for all s negative. So that's called an ancient solution. I should have said that already. Ancient solution, just meaning it's defined for all s negative, which is called a type 2 blowup. Okay. And then the theorem, the sort of main theorem in this subject that really makes everything work from what I'll say in my research talk, is the following theorem of Neves, which says, okay, what did we say? We said that you can't have self-shrinkers modeling the singularities, right? That cannot happen. So what's going to happen instead? That's what you have to ask yourself. If it's not that, then what is it? And that's what Neves proved. He said that if you have a finite time singularity, so at finite time singularity of 0 Maslov, LMCF, any tangent flow so this is like the first order approximation to what the singularity looks like. Okay? That's what the tangent flow is. It's like the first order approximation, like the tangent space. Any tangent flow is a union j equals 1 up to m, Cj, where the Cj are special Lagrangian cones with angle theta j, and the set of constants, theta 1 up to theta m, this set of constants does not depend on the subsequence. Okay, so you don't get uniqueness necessarily, but you get that these numbers are unique. So the angles that you get are always the same. Okay, so you always get cones. The cones might change, but the angles have to be the same, no matter what you do. And I should say, and the type 2 blowup, I said it was an ancient solution any type 2 blow up, sorry, any type 2 blow up is eternal, i.e. defined for all S in R. It's actually defined for all time. So if you do this, it looks like it's only defined for negative time, but you can prove that in fact, in this case, it will always be defined for all time. If you'll allow me the indulgence of 1 more minute, then I'll stop. So this is very good because it says that the tangent flow looks like it's special Lagrangian. That's great because that's what we wanted to converge to, right? That sounds like we've basically solved all of our problems. But it's not as simple as that, unfortunately, as I will explain next time, because there is also another candidate for what could happen. So the question is, what could the type 2 blow-up be? What could type 2 blow-ups be? So the obvious answer is a special Lagrangian, but another answer, so it can't be a shrinker, right? Because shrinkers are only defined for negative times. So it can't be a shrinker. It's got to be something else that's defined for all time. Another answer is what's called a translator. So this is where H is V perp for V in Cn constant. And that's the same as saying that LT is L plus TV solves LMCF. So it just translates in the direction of V. That's the thing. And the lemma, another exercise for you, the final exercise, is the following lemma. It says that L is a zero Maslov translator if and only if there exists a coordinate W on R2n such that, so it's a real coordinate W such that W is in the span of 1 and theta, i.e. it's a linear combination, so W restricted to L is in the span of 1 and theta. It's a linear combination of a constant and a constant multiple of the Lagrangian angle. That's another easy exercise using the definition. You just put J grad theta is here, J grad W is there, basically. It's not quite that, but it's basically that, and that will tell you the answer. But this is a very nice fact. Again, we've reduced it to a scalar problem, right? All of these things, we keep reducing them to scalar problems, and that's really good. So even though translators, they sound scary, they're not because of this sort of fact. And so what we have now, to conclude, is we have a good structure theory, at least, for what singularities should look like. Now we have to prove that's really the case. This is just giving us the first order approximation. We have to then prove what really happens in the flow, what is actually happening. And that's what I'm going to talk about in examples later today. Thank you very much for your attention.
All right, any questions for Jason?
Oh, yeah. Oh.
So why is
Yeah, because we know that the tangent flow is already special Lagrangian, or it's a union of special Lagrangians. So whatever this thing is, asymptotically, it should be special Lagrangian, whatever the thing is. It has to be that, right? Or a union of special Lagrangian cones. That should be the asymptotic model. And the most obvious thing you can think of is it's just a special Lagrangian which is asymptotic to one of these cones. And it's obviously an eternal solution. I also need that, right? It has to be an eternal solution, as be defined for all time. Well, if it's stationary, it's definitely defined for all time. And it's going to have the right asymptotic behavior. Yes, so yeah, that's right. So it's related to the question that I was asked by Franz, which is, as I said, something like this could be the tangent flow, right? Because that's just two special Lagrangians. Each of them is individually special Lagrangian, but the union is not. And there's definitely no special Lagrangian asymptotic to this, no way. In particular, you could just take just two lines the same. This could also happen. And again, there's going to be no special Lagrangian asymptotic to this other than the lines itself. But there will be a translator that's asymptotic to this. So that's going to be the problem, that we can have translators that are asymptotically special unions of special Lagrangians, and they're not going to be special Lagrangian for sure. So that's sort of our main enemy. We can't prove that that's the only thing that can happen, but as I'll tell you in my talk on Monday, there are cases where we can show that that is the case, that in fact, the only thing that can happen is it's either special Lagrangian or a translator, nothing else. So that would be, but that's very nice, right? That's not what you'd expect. It could be anything at this point, but it's definitely, in some cases, you can show what I said is true. Yep. Yep. Yeah. Yes, so it's moving. Yeah, so it's a moving one. Yeah. Yeah, it does, but it doesn't tell you as much as you'd like. The problem is that for curves, it tells you everything, but not in higher dimensions. So what you should think about it is like, so suppose I had two planes in Rn meeting transversely. How many angles do I need to prescribe to tell you one plane from the other? Well, there are n of them, right? There are n angles, right? And what the Lagrangian angle is the sum of all of those angles. That's what it is. So as the dimension goes up, it's telling you less and less and less. So in dimension 1, it tells you everything. Dimension 2, it's telling you something. Dimension 3, it's already quite hard. And above that, it's not really telling you anything. So this is the main difficulty about special Lagrangians, this whole business, is that the Lagrangian angle, although it's great, it's telling you less and less information as the dimension goes up. So that's the big difference. Like hypersurfaces, kind of, it doesn't really matter once the dimension, I mean, dimension 2 is special, but then all of the hypersurface theory is basically the same. Mean, convex, doesn't matter. It's just always the same. But here you really see that the complexity of the problem is increasing as the dimension goes up. So it's a lot more like Ricci flow, which is getting more complicated as the dimension goes up. It's like that. Yeah. Or Kähler-Ricci flow. Yeah.
For the Nevis result, is there anything that can be said about the special Lagrangian cones, like what the links are?
No, you can't say anything. Well, I mean, okay, so again, in low dimensions, yes, but in general, we don't know anything. Like it could be anything. Like even if you did this in dimension 3, so if you just take special Lagrangian cones, 3-dimensional ones,
right,
every genus is possible for the link. So, and we know that they're ones of arbitrarily high genus. I mean, it's just, anything can happen basically. So there's nothing you can say. You can't constrain the topology of these at all. I think in general, there's very little you can say about this. Like if you want to say something topological, that's very rare. But what you should be able to say is that you should be able to say that the ones which are topologically complex should somehow be rarer. That should be possible. Rarer. Like you should be able to do some kind of generic, like I think Felix has been talking about this generic regularity stuff. So you should hope that if you do a generic Lagrangian mean curvature flow, so if you perturb the initial conditions a little bit, you should be able to get rid of a lot of the singularities the ones with high genus, the ones that are topologically complicated, they should all disappear. And you should end up just with the simple ones. That's somehow the dream. But might be true. I mean, like it seems to work in mean curvature flow, but of course, Lagrangian mean curvature flow is very different because there you're always working with perturbing away self-shrinkers. You already know that self-shrinkers are the only thing that happen generically, and then you have to perturb the way. Here, self-shrinkers are not even generic. They don't even happen. Full stop. So that's a very different situation. I mean, the ancient solution, I mean, the type 2 blowups, they don't satisfy any elliptic equation. They just satisfy a parabolic one. That's very different from the self-shrinker case. Right? Self-shrinkers satisfy an elliptic equation. That's very different. Yep.
Theorem where you said the Lagrangian is preserved under mean curvature flow for the if you start with a combat surface. So what about non-combat one?
Yes, so that's a great question. So if you have a smooth Lagrangian that's say asymptotic to a cone or asymptotic to a cylinder or something like that, then the same thing's going to be true. Basically, as long as you can apply, and the asymptotic is good, like it's a special Lagrangian cone or it's something nice, right? You have some control on the asymptotic behavior, and you know that the volume growth is no more than Euclidean or something like this, right? You need some control like that. Otherwise, you can't apply your standard parabolic theory. A harder question is, suppose it's non-compact in the sense that it's compact but with a singular point. Now, this is much more difficult. So this we don't know. Like, it looks like sometimes the Lagrangian condition will be preserved and sometimes it will not. So it's actually not clear. It depends on the type of singularity. Like sometimes you could keep it. You could have a special Lagrangian with a singularity flowing. So that was proved by Tapio Berndt. So you prove that that can happen. But there are also cases where you can prove that the Lagrangian mean curvature flow would develop a singularity through which it could not stay Lagrangian. It would be impossible. So the mean curvature flow can continue. So that was shown by myself and Felix Schulze that we can continue this flow, but it's not going to, you cannot stay Lagrangian. It's impossible. Like, there's a solution to mean curvature flow where it starts Lagrangian, is Lagrangian until the singular time where it's still Lagrangian, and then will stop being Lagrangian after the singular time. So that is, yeah, that's much more complicated.
So in that case, can we get a self-shrinker, like non-combat self-shrinker?
You want a non-compact self-shrinker Lagrangian?
Yeah.
Oh yeah. That you can have. So you can have Lagrangian self-shrinkers. They just can't be zero Maslov. So I mean,
okay.
Yeah. So I'm going to write down next time some Lagrangian self-shrinkers for you. They're going to be very easy, but yeah, they exist, but they can never be zero Maslov. Like this. Okay. So strictly speaking, the theorem that I stated by Mutao, it was over there, the Mutao-Ouyang Nevers result, it uses something like you need at most Euclidean volume growth and something. So it might be possible if you have like exponential volume growth or something, you might be able to do it. But, okay. And if you allow singularities, for sure you can do it. Yeah. Okay. Yeah. If you allow it to be singular and have this very large volume growth, then you can do it. Yeah. I think there are examples actually that look like that. But if you but those things could never appear as a tangent flow. Mm-hmm. So then they're not that interesting from a flow perspective. They exist, but they could never appear.
So even in non-combat case, it cannot be.
It cannot. Well, I mean, again, if you impose something like at most Euclidean volume growth or something, then it could never happen.
Okay.
Yeah. But even if you had something that wasn't Euclidean volume growth, it's probably hard to say that mean curvature flow even exists. Like you need some kind of control, like to even get mean curvature flow to start. A lot of the theorems about mean curvature flow, Huskian monotonicity, all these things, they always assume at most Euclidean volume growth. Yeah. So you're never gonna, I don't think even the mean curvature flow really makes sense if you start doing this exponential volume growth stuff. At least in Euclidean space. I mean, of course, in hyperbolic space, this might be the right thing to do. Here, it's not the right thing to do.
Thank you.
Okay.
Any other questions?
So does Lagrangian submanifolds also remain Lagrangian under this mean curvature flow?
No, so that's a very good question. The question was about Legendrian. So Legendrian is the odd dimensional analog of Lagrangian. So if you take a Lagrangian cone, then its link is Legendrian. And you can ask, if I run the mean curvature flow, does a Legendrian that starts Legendrian stay Legendrian? And the answer is no, in general, it won't. And the way that you can see that is because if you take a Lagrangian cone and run the mean curvature flow, then what it should do is instantaneously smooth it out. Right? So it should not stay a cone. And that's going to break the Legendrian condition. So, but you can do, there is a Legendrian, it's called the Legendrian mean curvature flow, although it's not really. You can project the mean curvature vector back to the Legendrian deformations. But then it's got a non-local term. So there is a theory. There are papers about it. So Smoczek wrote a paper on this. And there are a few other people who studied it, but it's not strictly speaking mean curvature flow. And it has this non-local term in it, which makes the analysis more difficult. You have to do like a harmonic projection type thing.
Thank you.